This video is on Graham's law of diffusion and effusion. The two terms have slightly different meanings. One means to spread out, one means escaping through a pinhole. In terms of the problems you're going to get, there's going to be no difference in the math or in the application, so I don't want to focus on that. Now, the law states that the velocity of a pair of gases, the difference in the velocity, or the ratio of the velocities, is inversely proportional to the molecular mass. Now, this formula is not on the AP reference tables. However, it's easily derived because we're assuming that the gases are moving at the same temperature, so therefore they have the same amount of kinetic energy. So you have kinetic energy of gas A and kinetic energy of gas B. And because of that, you can assume that 1/2 the mass times the velocity squared for A is equal to 1/2 the mass times the velocity squared for B. The halves can cancel out. And what you can do is move things around. I'm going to put little A's down here and little B's down here. And then I'm going to move things around. So there's two versions of this formula. All right. The first version would be this. M of A, all right, over M of B equals the velocity of B squared over the velocity of A squared. The other one involves taking the square root of the two sides. So you would have square root of the molecular mass of A over square root over molecular mass of B equals V of B over V of A. So what are the values of the two different versions of the formula? Well, in this version, if you're given the relative velocities, or even the distances they travel in a set amount of time, because they're proportional to the ratio of the distances corresponds to the ratio of the relative velocities at a given temperature. You can plug those numbers in here, and if you know, let's say, if you know the molecular, like you know this one's neon, let's say, and you're trying to figure out the molecular mass of the other gas, well, you've got this number here, and you've got this number here. You can use this formula to get a molecular mass. So this is the second way that we can determine a molecular mass that we've talked about just in the gas law unit. So you can use pith unit and volumetric analysis in the dRT over P formula to get a molecular mass. Or you can use the relative rates of diffusion or the relative distances they've traveled and plug them into this formula here to get a molecular mass. This other formula is more useful for determining how much farther a gas will travel or shorter than a gas will travel, or how much faster one gas is than the other. So if they say one gas is going at 5 meters per second, how fast is gas 2 going to go? Or this gas traveled 10 meters in this set amount of time. How far will this other gas go? All right, let's turn the page and do a few quick problems. So let's start with oxygen and chlorine. And let's assume that chlorine's given mass is 71 grams per milliliter, oxygen's 32 grams per mole, and we have chlorine traveling at a rate of 5 meters per second. So how fast will the oxygen go? Now, it's good to walk into these questions with an idea of what you're supposed to get. Oxygen weighs about half of what chlorine weighs. It's going to be moving faster. It's not going to move twice as fast because it's inversely proportional to the square roots of the molecular masses. So we're going to have to use a formula. We have to pick which formula we want. Since we want velocities, all right, we want to go with the second formula over here because we can put in our gases inside that bracket and it will give you their relative rates of diffusion. So I'm just going to take this part of the bracket right here. I'm going to put the molecular mass of oxygen on the bottom, 32, and the molecular mass of the chlorine on the top, 71. And this is going to give me the rate of the velocity of oxygen compared to the velocity of the Cl2. Notice the flip-flopping of the equation here. When I figure that out, I get 1.489. And what that means is that basically the oxygen, okay, is going 1.489 times faster than the Cl2 is going. And so once I'm done with using this formula, I can go back to direct proportions. And that's really what you want to do. Use the formula to figure stuff out. And then if there's anything about speed or distance, go back to just a direct proportion. So I can just set up a really simple situation where it's 1.489 for the oxygen compared to 1 for the Cl2, and I go X for the oxygen, and the chlorine's moving at 5 meters per second. And I basically cross multiply. And when I do this, I get 7.45 meters per second, which makes sense because that just means 7.5 is about 1.5 times greater than 5. Honestly, if you just want to multiply it out, as long as you understand what's going to happen, clearly the oxygen is going to be moving faster than the chlorine. And if you accidentally divide it, you'll get a smaller value, which would not be sensible given our understanding of masses at the same temperature and how fast things move. Okay, example 2 would be one where you're given distance. And it's kind of the same exact thing. If oxygen travels 10.5 meters, right, how far is the chlorine going to travel? Well, we know that 1.49, that's 489, I'll use that. Okay, I'm not doing sig figs, obviously. Meters for every 1 meter that the chlorine travels, right? I'll say that again. We know that oxygen is going to travel 1.49 meters for every 1 meter that chlorine travels, right? So if, right, the chlorine travels, if the oxygen travels 10.5 meters, how far is the chlorine going to travel? And we can cross multiply this thing out, and this time we're going to have to divide, and I'm going to pause because I left my calculator in the other room. And so in the same amount of time, the chlorine will only travel like 7.05 meters. Now notice, I didn't bother going through this thing because once I knew how much faster the oxygen is than the chlorine, right, I can use that in separate proportion. This is not just a ratio of speeds. This says that, for every 1 meter that the chlorine travels, the oxygen is going to travel 1.5 meters. So we can just set up a ratio, a direct proportion, and solve the problem. Nice and easy. And that's our answer. Now, the last thing that you might use this for is to determine a molecular mass. So that's on the next page. So imagine you have a situation, right, where you don't know what the other gas is. Like, we know it's chlorine, but because we're using all the numbers from the previous slide. But let's say I was giving this question to some new students, and they didn't know, and chlorine is our X. So how does this work? Well, all you have to do is really stick the values into the equation. So I'm going to put the speed that the oxygen, I messed this up, this is the oxygen is traveling this fast, and the CO2 is traveling at 5 meters per second because the oxygen travels faster. So I'm going to put the oxygen on the top, so I put the 7.45, and I don't need the units because they're going to cancel out anyway because they're in a ratio, right? So I really have 7.45 over 5, I'm going to square that, right? And that's going to be equal to the X, which is the chlorine, right? See this inverse relationship here again, right? Right, because that's the chlorine down there, and this is we're going to find this is X, which we're going to find is chlorine. And on the bottom, we've got 32, which is the formula mass of the oxygen. So when we square this thing and we do the math here, so we do, I'm taking out my calculator, so we get 7.45 divided by 5, and then we take that number and we take it and put it to we square it basically. So we get like 2.22 whatever equals X over 32, and so we just times that by 32, and that gives us, so X is equal to 71.0, which, if they give you in the question, it is a diatomic element, that is a gas at room temperature. Which diatomic element could it be? Well, it certainly can't be like fluorine or nitrogen, but it could be chlorine, and so that would be the correct answer because the formula, this is the grams per mole for that substance, and that only matches the chlorine.